On today's show, robots and how they operate. A forensic science investigation, and IC's in trouble again, all on Hot Science.
Hi, welcome to Hot Science.
Hello, meet our duck Quack.
Now, Quack is the coolest little beast. He just sits there bobbing up on the pond, but hang on a tick, let me touch him. He's not there. What if I did this? Ah, look, I can pat him. But Sue, look what's happened to my arm. I've put it in and it's coming straight back up. Can you see?
Ah, it's all an illusion, is it?
It is, I think. What's happening?
Well, if you want to see how this trick works, come around the side and I'll show you. It is all a bit of an illusion because the duck wasn't up on top here at all. The duck's hanging upside down from some string.
And it's plastic.
We wouldn't do that to a real duck. And the illusion is caused by this special mirror here, which is curved. You can see on one side. It's actually curved inwards, and it's called a parabolic mirror. And because it's not a flat mirror, we get that illusion. Because the light from the duck travels to here, it doesn't get reflected straight back like it would off a flat mirror. It actually gets reflected up here at an angle because of the curved mirror.
Now, could I do that? Could I hang upside down and be
look,
up
we
here?
could, yes, if you'd like to give it a go, we'll do it.
I think we'd need bigger poles there, but I'd never be able to touch the duck.
No, because it's never really there. It's all an illusion caused by a parabolic mirror.
Action and reaction.
Ow! Sue, you scared me.
I did. I got a good reaction too. That was just one type of action and reaction.
Right.
There are plenty of others. Are you
Yeah?
interested in them?
I sure am.
Okay, well, we can do an experiment with the balloon.
I love balloons.
But before we do that, I'm glad you were interested in actions and reactions because there was a very famous scientist called Sir Isaac Newton. And he was interested in actions and reactions too. And he came up with 3 very famous laws.
Yeah?
And the third one is the one that we're interested in. And this law says that when 2 objects interact, say if one collided with another, for every action, there's an equal and opposite reaction.
Oh,
I knew it.
I knew that.
Okay, well, we can do an experiment with this balloon.
I love balloons. We can have a party.
Okay, all
Hey,
right.
Sue, did you bring my present?
What present?
Oh, I'd like a bigger bowl if you could.
Well, you can just stay there for the time being. Let me blow this balloon up, though.
Okay. Oh, you're full of hot air there, Sue.
Big enough?
Yeah, a little bit more, a little bit more.
I
That's
thought
the
you'd say
way.
that. Okay, now, what we're going to do is let this balloon go.
Oh, great.
Okay, I'm going to let it go that way. Would you like to hold it?
Yeah, let me.
Okay, I thought you would.
Okay.
I'll just hold your hand up
Yep,
here.
yep. Oh,
Now,
that's it.
hold on.
Yeah,
Have
I've
you-
got it. Yeah.
Have you got it?
Okay. And can I get the countdown?
Before we do that,
Ah.
we've got to explain what we're going to do. Now, you know
Okay.
what's going to happen when I let
Yeah.
this balloon go, don't you?
Yep. Hey, it's going to go.
All over the place. That's right. As the air comes out this end and pushes this way,
Right.
the balloon gets pushed that way. That's the equal and
Yeah.
opposite reaction. Are you ready?
Okay, yeah, ready. 3, 2, 1, go!
Whoa!
Whoa, there it goes. Look at
That's
that.
a good launch. Now, real rockets
Yeah.
work on the same idea. Shall we have a look at one of those now?
Yeah!
Ignition. Liftoff. Liftoff. 30 minutes after the hour.
Wouldn't it be wonderful if we could protect ourselves from being touched by certain things, like if there was a thunderstorm, rain's coming down and we didn't want to get wet, all we'd have to do is hide ourselves like this and we'd be protected? Well, that's exactly what this little plant does. It's called a mimosa, and have a look at this. If I just touch this little leaf here, it's collapsing. I'll keep touching the leaves. If I run my finger down the centre, look at that, it's closing up. Now what if I do it to the whole stem? Touch it down here. They're all collapsing. Down there like that. Now what's happening is as I touch the plant, that touch is being converted into electric impulse. So the impulse travels from the touch point on the leaf down to the base of the leaf, down here, where there's a tiny little water sac, like a little swelling. And that impulse tells the water to release. Now, without any water in it, the leaf just collapses. Now, there's also little water sacs at the base of each leaf and at the base of the stem, so that the whole plant can collapse once it's been touched. And it does that to protect itself from insects or animals and things to being eaten. Then when the plant senses that everything's okay and the predator's gone away, the water flows back up into those water sacs. It fills up, the plant once again opens, and you get it back to look like this. Now the plants can grow from about this size, this is a pretty small one, up to huge bushes that sort of come out here. So the next time you're in a nursery, why don't you check out a mimosa?
Next, your chance to create delicious chemistry. The Adventures of IC and Poot. IC had completed his homework assignment late in the evening of June 15. It was due the next day. He had written it out on one page of his thick homework pad. He slept soundly that night, knowing all his work had been completed in time. That same night, Poot felt a little hungry and decided to make a midnight meal out of IC's homework paper. IC noticed the missing document the next day. What could he do? How could he retrieve the missing information?
Oh no, did you see IC? There was smoke pouring out of his ears. He looked like he was going to explode. Has that ever happened to you? You've lost your homework and you've really needed it? What would you do? Unless you'd videotaped it the night before, I can't think of anything. Well, we have our team of investigators over here. There's Lucinda and Erin. Have you written a secret message?
Yes.
Should we show everyone?
No.
You sure?
No.
Okay, let's get rid of them then. Whip that one up there, Erin. Yep, sprinkle it up. Well, Lucinda, how do we get our message back?
Well, you get your pencil and colour hard over your message.
Mm-hmm.
And then when you finish colouring hard over it, then you will be able to see it.
Oh, yep. Let's have a look. What was your message, Lucinda?
I love chocolate.
And there it is. Well done. Do you like chocolate?
Yes.
What's your favourite? Mine's
just-
milk.
I
Milk
just like
chocolate?
all chocolate.
How's yours going, Erin?
Good.
Can we read that? My birthday is in September. How old will you be?
I'll be 11.
Well, happy birthday for September. That's one way you can get back information. Here's a forensic scientist with another.
Have you ever written a secret note? It's good fun. You just write down your secret, tear off the piece of paper and send it to a friend. But these days a forensic scientist like Ian Riebling can take the piece of paper from under your message and find out your secret.
With this piece of paper, it looks like nothing is written on it. But in the world of forensic science, we're able to find out what was written on it.
Forensic scientists specialise in working on evidence for court cases. In this case, they're using a machine called an electrostatic detection apparatus. First, they cover the paper with a piece of plastic called mylar, and it gets sucked down tight by a machine very much like a vacuum cleaner. Then they use an instrument called a corona to charge the plastic with what's called negative potential, making it sort of like a magnet, which works strongest in the dents left in the paper where the person who wrote the note pushed down on the pen. Now this is called photocopy toner. It's used in photocopying machines, and the scientists mix it with glass beads to help it slide around better. They sprinkle it on and it sticks to the plastic, held there by the magnetic force. It especially shows up those dents. And after a while, it slowly reveals the words of a once secret message. And there it is, for everyone to see. Then more plastic is placed over it to protect the vital evidence.
In the world of forensic science, this allows us to see what has been written on a missing sheet of paper.
Wow, that's amazing. Hey, aren't forensic scientists clever?
Sure are.
Yeah, hey, Sue.
Yes.
Have you finished my letter to Angel yet?
Who is Angel?
Oh, you know, Angel, my girlfriend.
Angel as in angel fish?
Yes.
Oh, okay. Well, yes, I have finished your message and I made it out of invisible ink.
Yeah?
And here it is.
Sue, bit of a problem there.
What's that?
How's she going to read it? There's nothing on the paper.
Well, I used invisible ink like you told me to. There's just one thing I need to check, though.
What's that?
Well, that's how you spell ooze. How do you spell ooze? How
It's got 12 O's in it.
Well, oh no, ooze. I only had room for 4, so that's all I've put in.
Oh, that'll do.
Will it?
Ooze. Yeah,
Okay.
great.
All right,
Hey,
well-
I think we'd better check it, Sue, because knowing you, there'd be plenty of spelling mistakes.
Ooze, I didn't make any mistakes, I'm sure.
You sure?
I am.
No, we'd better check it, Sue.
Well, there's only one way to make the message appear.
How's that?
Well, that's to heat up the piece of paper. You sure you want me to make it appear?
Yes, we
Okay,
better.
well, come over here. You've wet it a little bit anyway.
Oh, sorry.
But to make the message appear, what I can do is use an iron.
Oh,
And if
an
I iron over the message,
Yeah,
you watch as it appears. You can hear it sizzling from the water you just put on it.
right.
And we iron away.
Oh, yeah.
And I made the invisible ink out of lemon juice. That was all it was. And the lemon juice, when I painted it on the page,
Yeah.
reacted with the starch in the paper.
Oh,
And as it reacts, it breaks the starch down into simple sugars, like brown sugar. And that's why
Right.
we get the brown colour.
so then we can see the message.
We can. I just need a little bit longer to make it appear.
Okay.
I think it might be just about enough for you to see, though. If you were going to do this sort of message, you need to make sure that you had a grown-up to help you with the hot iron. Okay, well, I've got the message. Do you want to have a look?
Yeah, sure.
There we go.
Oh, you've drawn
Doesn't
it on
say
there.
very
That looks
much, does it?
great. Yeah. Hey, do you want me to tell you what it means? Because
Yes.
she understands, but you probably don't.
No, I don't.
It says, "Dear Angel, meet me at the lily pad. Ooze." She'll love it.
Well, I could send that. Oh, no, I
No,
can't
you
send
can't
it now.
send it. Now you're going to turn it back to invisible ink.
Well, I can't do that. I'll have to start all over again. But while I'm doing Ooze's letter again, why don't you try making some invisible ink and sending somebody a message?
This robot can do your homework, play music, make your food, and comes with a blow-up car. You can tell him to do any work you want him to do.
What a neat robot. Wouldn't it be good to have robots to do all the horrible things we have to do?
Oh, it would be good, but I still like doing things myself, like cooking. What's your favourite food, Sue?
Well, I like chocolate.
Do you like ice cream?
I love ice cream.
Well, we are going to make some ice cream. Now, Sue, I understand how to put all the ingredients together, but I don't know what the science is in it.
Well, let me help you out.
Yep.
First thing we need to make ice cream is to cool down the ingredients. And what we're going to do is use some ice to do that. And if we have a look at the temperature here, I've got a digital thermometer, and down there
It's
is
about minus 0.7.
Oh, okay. So it's around about 0 degrees, isn't it? Now, to make ice cream, we need to cool down the ingredients much lower than that.
Like to what?
Or about minus 15, minus 20 would be good.
Oh, okay. How are we going to do that? Put it in the freezer?
Well, you could do that, but a much more fun way and a much, much quicker way is to use a bowl like this filled with ice and just make the ice colder.
By?
Well, by adding salt. And I've got a big bowl of salt here. You need to add quite a lot of salt to our mixture of ice. Do you want to lift that container out?
Yeah.
And I'll add at least
Oh, you're going to be
one
all
handful.
salty.
Oh, I can feel it getting in my cuts. And if I might let you
Yep.
just
Oh,
mix that.
thanks a lot. No,
Okay,
that's
I'll give you a hand too. We need to mix the salt in really well. Oh, don't get any in our cream.
Salty cream. Okay, get on in there. Make sure it doesn't sink to the bottom. Ice is going everywhere.
No, that's good. We really need to mix that salt into the ice.
Oh, my fingers are cold.
You'll find that when you make this, the ice does get a lot colder. Right, well, we're ready now to make our ice cream. Let's get the ingredients together.
Okay, I put my little bowl back in the centre.
Dig a hole in the ice and the salt mixture.
Now, to make ice cream, we need a third a cup of cream. So I'll just, oh, look at that. Yum.
Yep, that will be plenty. So you put your cream in the container.
Just make sure I get all the gluggy
That's
bits
fine.
out. And 2 teaspoons of sugar.
Because we're making vanilla ice cream, aren't we?
Yep. And I'll just add some vanilla, and it's about half a teaspoon of vanilla. So this will probably be very vanilla-y.
Okay, they're all our ingredients ready. Then you need to stir your mixture up, and you need to keep stirring it very, very slowly for a few minutes. So give it a quick mix first. Mix all the
So put
ingredients
it all
together.
together, yep.
Yeah, really well.
Oh, it looks like caramel.
No, it should go all nice and creamy like vanilla ice cream. And now they're all mixed through, you just stir them very, very slowly. Perhaps
hold it there.
even that's too fast.
Really?
Yeah, really slowly like that. And remember to stir into the corners and the bottom. And if you keep that up for a few minutes, you'll have ice cream. And you'll know you've got ice cream there when you can actually lift the stick up and there's a glob of ice cream on the bottom.
Now, why do I have to do it really slowly?
Well, what we're doing here is we're freezing down the ingredients, and what we're going to form are very small ice crystals in the cream because there's water in the cream. But if we had big ice crystals forming, we'd have crunchy ice cream.
Oh, yuck, and it's all grainy and gritty.
Yeah,
Oh,
so you want to
okay.
stir it just so you've got ice forming, but only very, very small ice crystals.
Now, is the ice cold enough?
Well, let's have a look. What we might do first off is just mix this ice and salt together quickly.
Right, yeah.
Again, oops, there's our thermometer poking up. Mix that in. Oh boy, that's
Very
cold. I know it's colder than 0 degrees now. Let's have a look at the thermometer.
Okay.
Ah, look, it's gone down really
Wow,
quickly.
minus 17.8.
So adding the salt really does make the ice a lot colder. And it works because at the moment we've got a lot of water as ice. And when we add salt, that salt wants to dissolve in water, but it's ice at the moment. And to have this change from ice to water, we need energy or heat to melt it. Now, where is the heat and energy going to come from here?
Maybe the ingredient?
Well, yeah, exactly. The energy is drawn and heat is drawn from the ingredients and the ice and the bowl. If you feel that, the whole lot is a lot colder. And that energy and heat is used to melt the ice so that the salt can dissolve.
Well, Sue, I will keep stirring our ice cream very slowly, and maybe a little bit later on in the show, we'll get back and taste our very own ice cream.
Okay.
Next, robots and messages.
Robotics.
Robotics? Oh, robots are great!
Yeah, they are pretty cool, aren't they, Ooze?
Yeah.
But did you know they can't think for themselves?
Can't they?
No, they have to be programmed.
Oh.
Now, why don't you imagine yourself as a robot and then watch what happens when the programming details aren't quite right.
Move arm up into air. Squeeze out toothpaste. Take a sip of water. Begin brushing. Move arm up into air. Squeeze out toothpaste. Place toothbrush onto face. Begin brushing. Place toothbrush onto face. Begin brushing.
Now, you see, Ooze, robots can't think for themselves.
Yeah, I can see that.
But, Ooze, they are very important in industry and manufacturing. This is called a mechanical arm, and it can go places that humans can't go, and it can do it quicker than we can. Yeah, they're pretty important. Now, would you like to see some more robots working in action?
Oh, yeah, that'd be great.
Have a look at this.
This mechanical marvel is a robot, but robots are changing.
When people think about robots, they usually think of arms welding car doors together. But in fact, there are two sorts of robots, those that are like human arms and those which are mobile and move around on the floor in outdoor terrain. The second kind are the ones we're going to talk about mostly here. They have to solve 5 different problems all at once. Firstly, they need to know where they are. Secondly, they need to know where everything else is so they can avoid it. Thirdly, they need to be able to work out how to get from one place to another without bumping into anything. And finally, they need to be able to communicate back to a person at a home station that's giving them the next instruction. The Denning robot is the biggest one we've got. It weighs something like 200 kilos, which is about the size of a Japanese sumo wrestler, if you've seen them on television. It has the capability of working out where it is by using a sort of barcode reader. It can also work out where everything else is by having a laser scanner which measures how long it takes for a beam of light to get to an object and back. It works out how to move between the obstacles by using a planning method which sort of relies on finding the shortest path that it can take in the bits of the floor that it is allowed to move on. The Mobot, on the other hand, is a much more practical, primitive type of robot which has been designed specifically to cut lawns. We've got to the stage now where we can actually treat it as a radio-controlled toy that can move around and cut lawns. We can also make it move on paths which we tell it to beforehand by using a computer control with a single camera pointing down on some marks on the top. We are now about to do some outdoor experiments where the camera will be on top of a 30-metre tower, and hopefully the Mobot will be able to actually cut lawns and follow paths without bumping into the rockery or falling into the pool. We've got one robot that actually combines the idea of moving around in the room with that of having an arm manipulating things. And we're trying to do experiments like go to a certain place, look for a particular thing, pick it up and bring it back, sort of a fetch command. The last one we're going to look at is a very, very small robot, which is currently the smallest robot that is able to do something in reaction to an outside stimulus. In this case, it can follow a light beam. The robot is less than 1 centimetre cube, and although it's not very useful, it can't do anything sensible, it does represent what's achievable, and it's made out of 2 lots of watch parts minutely packaged into a small little shell with wheels and 2 eyes. Well, the future for robots, I think, is fairly bright. We're not likely to see anything that's going to take over the world, I'm afraid. But between these tiny little guys that the Japanese hope will eventually be able to go into the bloodstream to clean cholesterol out, to massive robots that are able to do construction and industry, the next 5 or 10 years should see all the basic research coming out of the research labs into sort of practical applications.
So for the future, we might even be able to see robots helping with the chores around the house.
Did you know an adult's eyeball is about the same size as a ping pong ball?
Quiz time, Rose. Here's one for you.
Yeah?
What's an example of an action and a reaction?
Jumping up and down on a trampoline.
Oh, yes.
And you wouldn't believe it, our ice cream worked.
Right.
So, you want some?
It's for me.
Oh, it's yum.
Hey, what about me?
Oh, okay, Ooze, open your mouth.
Oh, thanks.
That's lovely.
Give me some of the cone.
Not mine.
Oh, no.
Look, there's something for you to try. Why don't you make your very own ice cream, but maybe try chocolate, strawberry, vanilla. Oh, it'd be great.
It's time for us to go. We'll see you next time on Hot Science.
Bye.